Okay, I hope everyone can see the slide. Today topics is continue from last week. The topic of the chapter is harmonic excitation. And last week we learned about the harmonic excitation of the system without damper and system with damper. And we have a short introduction to a frequency response function. And today we will continue and review about the frequency response function. Last week we had a kind of homework for you and for myself because I still couldn't solve some solution. I couldn't derive some solution for you, and today we will complete it. Yeah, it seems like we have problem. How can we obtain the magnitude of the frequency response function? And we still have some concept that's still not clear about the phase angle of the frequency response function. So today we will complete this point. And yeah, after we have the function, we have the magnitude of a frequency response function, and we have a phase angle of a frequency response function. And today we're gonna know how to plot the magnitude and the phase of the frequency response function, the magnitude and the phase. And if you could remember, the frequency response function, the magnitude and the phase angle are written in the terms of the ratio. It may come into the terms like, for example, like this. It depends on the system, but yeah, most of the system, it seems like the frequency response function is written in the terms of the variable R. The ratio R is the ratio of the frequency divided by the natural frequency. So the natural frequency is the system property, is rely on the stiffness and the inertia of the system, and it is a constant for a constant parameter system. But the omega in the unit of the radian per sec is depend on the frequency of rotation of the applied force that apply to the system. And the frequency response function is a function of the omega, or the frequency of the input that apply to the system. Actually, the frequency response function is a function of the frequency of the input, and also is a function of the damping ratio. So today, for the frequency response plot, we will know for a constant, for example, for a constant damping ratio, how the magnitude of the frequency response function vary against the ratio R, or vary against the omega. because the omega n is constant, and also how the phase angle change depending on the ratio R. Today we will learn how to use the MATLAB tool to obtain the magnitude plot and the phase angle plot. And yeah, we will know how important is this plot, what is the meaning of the plot, why we need to plot the magnitude plot, and how the plot can explain the physical meaning of the system. And the Bode plot, actually the Bode plot is an alternative way to obtain the magnitude and the phase plot. The phase plot that we obtain from the Bode plot is the same, but the magnitude plot that we obtain from the Bode plot will be plotted in the different scale. It will be plotted in the log scale. And yeah, we will see. And the Bode plot also can be obtained from MATLAB also. And we will show the code and how to program, how to modify the program so that you can get the Bode plot for your system. But in order to obtain the Bode plot, we may need to begin with a transfer function. Actually, the transfer function is important if you want to deal with a transient response. Okay, Baton, I gonna share the today's slide for one more time. Let me check. Okay. You can say. I'm not sure you mean. Okay, in the today handout, this answer is answer to Baton. In the today handout, we will have some example of the MATLAB code and some plot, and you need to try to do the coding by yourself. Maybe you may just to replicate what I have written, and yeah, you need to try to run the program. But I won't share you the original code, but you can replicate the code. And if you have the problem to run the program, you can discuss with me after the class. And today we will go into the detail again, how to use the code in the today handout. I mean, today we have a lot of code in the handout, and I will tell you again how to copy the code and how to run the code, how to compile it on the MATLAB. So yeah, don't worry. And yeah, so in the early of the class today, we will review the frequency response function and know how to plot the magnitude and the phase plot for the system. And on the second half of the class, we will see some application of the frequency response analysis on the problem that relate to your study. The first type of problem is the rotating of unbalanced mass. For example, the vibration in washing machine, the vibration of engine that has the unbalanced mass. And the second type of the problem is the vibration due to the base excitation. So unbalanced mass, we may need to deal with a design problem, a design of vibration isolator. Sometimes we have a vibrating machine, and as an engineer, we may need to design some machine foundation that put beneath the machine and try to separate the vibration of the machine from the ground. And yeah, we will learn about this today. And for the base excitation or the suspension system of automobile, there are two things that we need to concern. Assuming that the contour of the road is a maybe sinusoidal function. Yeah, X and Y. The contour of the road may be a sinusoidal function, and your automobile is running with a constant velocity. So finally, if you plot Y against T, it also be a kind of sinusoidal function. And the frequency or the period of the signal also relate to the velocity here. If you drive fast, the period of the input signal also short. And the things that we need to do, we need to consider the displacement transmissibility. The displacement transmissibility means if the magnitude of the road contour is a constant here. For example, if the road contour has the magnitude about maybe 10 centimeter, the magnitude. The displacement transmissibility means when it transfers to the car and your car also move vertically, the magnitude of the vertical motion of the car, how is the amplitude of vibration. Although the road excitation has the amplitude of vibration, for example, 0.1 meter or 10 centimeter, it doesn't mean that your car needs to move vertically for 10 centimeter for all the time. And it also depends on how fast your car is running on the road. Sometimes, if you drive your car slowly, if you drive your car very slow, the wheel will follow the contour. And the magnitude of the X or the vertical displacement of the car will be the same as the magnitude of the road contour. But sometimes, imagine in the real phenomena when you drive a car on a bumpy road, sometimes if you drive it fast, if you drive your car fast, sometimes you cannot feel that your car is moved up and down. So sometimes if you go faster, although the wheel is follow the road contour, but your car not exactly move with the same magnitude with the road contour. So yeah, the real phenomena, if you pay attention to the car, when you drive the car, you may, before this, you may not know, but after this, after the class, maybe the next time you are going out from your home, and you sit on the car, you may try to pay attention to what happened to the suspension. If you drive slowly, sometimes you can feel that you are going up and down, follow the road contour. But if you drive the car faster, maybe you feel more stable on the vertical motion. The magnitude of the vibration may be lower when you go faster. But why? Every time we drive on the bumpy road, why not we just drive as fast as possible so that we don't need to see the vibration. We don't need to feel vibration on the car. Because although the displacement transmissibility is lower at high omega, at high frequency, but the force transmissibility, or the force that the road transfer to the suspension structure, the car body structure, and to the passenger, the force transmissibility is increased, sometimes increased with the speed of the car or the frequency of the vibration. So it's a kind of the trade-off between the comfort and, how to say, the damage to the structure. But as an engineer, your task is to design the spring constant and the damping coefficient for the suspension to match with the requirement of the system. Because in the real application, you will know that your car can move maybe from 0 km/h as a minimum speed, and it can go to maybe 180 km/h. And the road contour in general road, and you can, you can predict the maximum possible frequency of the road and also maximum magnitude of the road excitation. Yeah, you're gonna know the maximum omega and maximum magnitude, and your task is to decide the K and C for the automobile. I hope the screen still not turn to the black screen. If there are some portion of the screen, some area on the screen that turn to the black screen, and you cannot see the content, please let me know. Okay, last week we already talked about the frequency response function. The frequency response function relates the output force to the input force to the output. This output may be xt, and yeah, we said that sometimes if the input is written in the term of the cosine, and here we're gonna deal with the real part of the function, and on this side, on the output, we also still have the cosine. And if the input be a sine function, sometime during the derivation, we're gonna deal with the imaginary part of the frequency response function. Yes, and the output also appear in the function of the sine. Why not we begin, like try to begin from the the origin again. You have a simple equation of motion of a second order system. in an original terms of the system parameter, mass, damper, and spring. And yeah, if the input is cosine, we can assume that the response will be the real part of a complex number. We're gonna use the complex representation method. And by assume the complex number z, you can rewrite your equation of motion in the second order differential equation in the standard form, and also in the terms of the complex variable z instead of the x. So we're gonna divide the equation by the mass and then replace the x by the z. And yeah, the cosine is the real part of the complex exponential, and the full equation, if on this side we use the complex variable, the cosine for the full equation should be written in the terms of the complex exponential. And yeah, we assume that the complex variable z is a constant z multiplied by a complex exponential. So with this assumption, if we want to obtain the second derivative of the complex variable z, we can take the derivative of the exponential. So yeah, if we do the second derivative, the j omega will drop in front of the exponential as a constant for 2 times. So for the first term, what we have is we're gonna have j omega squared. And for the second term, we have only one time derivative. So we're gonna have j omega if we do the z dot. And for the third term, we don't have any result from the time derivative. So yeah, the left-hand side of the equation can be written by this. Yes, the z is a magnitude multiplied by the complex exponential. And when we do the second derivative, we can have j omega squared. When we do the third derivative, we have only j omega. And for 0 time derivative, we don't have j omega. And we multiply by the z. And on the right-hand side of the equation, yeah, it still be the same. So yes, if we want to find the magnitude z, what we have is we're gonna have f0 divided by m, and this term, and j omega squared is minus omega squared. So yeah, we can write it by the omega n square subtract by omega square of the first term. And for the complex terms, we're gonna have 2 psi omega nj. This is the constant, the magnitude c is equal to this. So if we divide by k on the numerator and divide by k on the denominator, I hope you still remember that the omega n is equal to the square root k divided by m, which means that the m divided by k is equal to 1 per omega n square. So we can, yeah, arrange the equation. So finally, it will equal to f0 divided by k, and this is 1 per omega n square. So we're gonna have 1 subtract by r square and plus 2 psi rj. Once we assume that the ratio r is equal to the omega divided by omega n, so finally we have the constant, the complex constant z, the magnitude equal to this. So we want to obtain the response, and the response x, we want to write the response x in the terms of the magnitude of the input force and magnitude of a complex function or the frequency response function and the function of the input. If we consider in this form, the frequency response function, for this case should be 1 per k of the terms of the ratio r. This is the frequency response function of this system. And in general, if we want to do the plot, if we want to plot the magnitude and the phase of this frequency response function, we may try to make the frequency response function to be dimensionless. So if we want to do it to be, make it to be the dimensionless, for this, we need to multiply it by a k, or the spring constant, to cancel with the denominator. And this is the way we derive the frequency response function in the terms of the ratio r. And if we want to turn it back to the the terms of the original parameter MCK. Yeah, we may try to do like this. How to write the frequency response function in the terms of the original parameter. So we will write the R in the terms of the ratio of the frequency and the natural frequency. And for the damping ratio, we know that the damping ratio is equal to C divided by 2 square root Km. And R is also omega divided by omega n J. And yeah, it should be, if you multiply K into the parenthesis here, you're gonna have K, and K omega square divided by omega n square is K divided by M. And the second term here, what we still have here, when we multiply it by K, it's gonna be C divided by square root Km and multiply by K. And once we know that the omega n is square root K divided by M. Yes, finally, the frequency response function, if we try to, yeah, K can be removed. And here we have K and square root K. And this gonna be M. Oh no, M will be cancelled with M also, because this is square root K divided by M. So finally, if we want to write in the form of original parameter, we have the frequency response function in the terms of K subtract by M omega square for the real part, and for the imaginary part, we have C and omega. We have two choices. We're gonna write it in the terms of the ratio R, or in the terms of the original parameter of the system, MCK. But please remember this form. Last week, we still have problem how to obtain the magnitude and the phase angle of the frequency response function. So the frequency response function in the terms of the ratio R is equal to 1 per K of 1 minus R squared plus 2 psi R J. So we multiply by a complex conjugate of the denominator. the complex conjugate is this divided by the same 1 subtract by r squared and 2 psi rj. Yeah, the complex conjugate, we have the plus and the minus here. And once we compute the product of the denominator, the product of the denominator will be the first term square subtract by the second term square. So it's gonna be 1 and square, and the second term and for the numerator, we still keep the same function. And we can still do a few more things for the denominator, because the j square equal to -1. So what we have here is 1 subtract by r square, and j square is equal to -1. So this is a real number, no more complex number in the coefficient here. And for the second term, yeah, we still have the real part and the imaginary part. So the magnitude of the frequency response function we know that if a complex number a plus bj, the magnitude is a square root, a real part square plus the imaginary part square. So for the frequency response function, this is just a constant, a real value constant, and we have a real part and a complex imaginary part here. So if we want to find the magnitude, we just do the square root of the real part square plus the imaginary part square. Oh, I'm sorry. So the real part square will be 1 subtract by r square. And the imaginary part square is and yeah, this will divide by the constant, which is so can you see some hint here? So finally, the magnitude of the frequency response function is 1 per k, and these are the same. I mean, inside the parentheses and inside the square root are the same things. So we're gonna have 1 subtract by r square and square and this will be 2 psi r square. So this is the magnitude of the frequency response function. For the phase angle, of the frequency response function should be the arctan of the imaginary part and the real part. So the imaginary part is this term. Don't forget the minus sign here. So imaginary part is 2 psi r, and the real part is 1 subtract by r squared. So now we have the magnitude and the phase angle of the frequency response function. If we want to plot this on the MATLAB, the structure of the MATLAB, what I did here is we have the magnitude plot, the magnitude of the frequency response function, and the phase angle of frequency response function as a vertical axis. For the horizontal axis here is the ratio R, which is the ratio of the omega divided by omega n. And to do the plot, I try to assume the damping ratio to equal to 0.1 and do the plot. Assume the damping ratio to be 0.5, to be 1 per square root 2, and to be 1. And the magnitude here is what we derive here. The magnitude, but yeah, the magnitude of the H omega, or the frequency response function, actually is equal to 1 per k of the square root 1 subtract by r square and plus 2 psi r square. This is the magnitude. And the phase angle of the frequency response function is equal to the arctan of the minus 2 psi r and 1 subtract by r square. Okay, you can confirm this with this. The magnitude is this one, and you just want to plot the magnitude in the MATLAB. And the phase angle is this one, and you want to plot it on MATLAB. So what different here? This one is not dimensionless. If you want to do the dimensionless, you multiply the frequency response function by a spring constant k. So this is the reason why the coefficient here is just only 1, not 1 per k, because we just want to make it to be dimensionless. And to transform this square root into the MATLAB code, we transform to this, the square root and the damping ratio here. And for the phase angle, we use the function arctan 2 so that we can get the quadrant of the angle. But we have D here, which means that the MATLAB will compute the angle in the unit of degree. If you use A tan 2, it will be in the unit of the radian. If you want to get it in the degree, you use A tan 2D. And be careful, this is a comma between the first and the second parameter that you put into the function. We have a comma, not a slash. And the structure of this program, what I did is you need to do it manually. In the beginning, I open the comment here. In the beginning, I open the comment here. And the damping ratio will equal to 0.1. And I close the comment here. And the ratio R will be vary from 0 to 10. And yeah, 10 is 10 power 1. But 0 can be go to the left-hand side, but the plot just begin from 0.01. And yeah, I set the parameter R to be vary from 0 to 10. And the magnitude, the variable to store, the magnitude has the same dimension with the variable R. The phase angle also has the same dimension. And in the for loop, the for loop will run from the first value in the array until the length of the variable R. And yeah, in the for loop, the R will equal to the value of the frequency ratio. So if I equal to 1, the ratio, which is one constant value, will equal to the value that's stored in the room number 1 of the array variable R. So it will be 0. And in the second loop, it will be 0.01. In the third loop, it will be 0.02. By set this parameter, it means that the R will equal to 0, 0.01, 0.02 until 10. And yeah, this will be R when I equal to 1. This will be R when I equal to 2. So we're gonna have R for each value that's stored in the array of the R. And for each R, when it runs the loop, we compute the magnitude that corresponds to the R. We compute the phase that corresponds to the R for all the value of the R. So when we complete the for loop, we can get the value of the magnitude that corresponds to the R. And we can get the value of the phase that corresponds to the R. But just for the theta equal to 0.1. And I put the plot command. The plot command here is new for you. it's not begin with the plot, but I begin the command with subplot. By this, the subplot to 1, you're gonna have 2 rows of the plot, the first plot and the second plot here. And the number here, you're gonna, how to say, indicate you're gonna plot in the first or in the second. You may try to do subplot to 2. If you do subplot to 4, what you're gonna have is you're gonna have 2 rows and 2 columns. And number 4 here will be plot in here. 4. This will be 1, 2, 3, 4. If you do subplot 2 to 4, you're gonna have 2 rows, 2 columns, and you're gonna indicate the plot that you will put the plot into by this number. If you change this to 3, the plot will be in this window. Yeah, so in our case, we have subplot to 1, which means we have 2 rows and 1 column of the plot, and 1 indicate the first, 2 indicate the second. And instead of using plot function, I use the function semi-log, and the semi-log of x, which means that on the horizontal axis of the plot, it will be in the log scale. So if you put the function semi-log y, you can predict that the semi-log will be on the vertical axis. But here, semi-log x means, yeah, the log scale is on the horizontal axis. And you're gonna plot the value of r against the magnitude. R will run from 0 to 10, and magnitude has the same dimension of the array and have the value of magnitude that correspond to the R. And it will plot the blue one here for the magnitude plot. And for the phase angle, we do the same thing, but the phase angle will be here on the second plot. After I put this on the MATLAB, I redo it again, but I close the comment. I put the comment here, and I remove the comment for 0.5. And now for the second plot, the damping ratio is 0.5. And I plot it again. So after I copy and paste for the second time, we have the blue and the orange plot. And I redo it for 4 times. So finally, we have 4 lines in each plot. And what you need to concern is the comment before the regen command. The regen command will plot this block for you and tell you the name of the dataset. So imagine that if you just plot the first line for the damping ratio 0.1, if you don't put the regen command, don't put the comment for the regen command, the program will try to find the data set for 4 data sets. We have 4 data sets here. But you have only 1 data set, so it will show the error. So your task, you need to consider where to put the comment here that correspond to the damping ratio. Begin from 0.1, 0.5, and for the first 3 plot, you may better to put the comment for the legend line so that it doesn't plot the legend. But on the final round that you plot when the damping ratio equal to 1, you open this line and it will have the complete plot, and you will see this. And yeah, what is the meaning? What is the meaning of the frequency response plot here? If you see the plot, you can see that the damping ratio has no effect at extremely low and high frequency. You can see the effect of the damping ratio between this region. But at low frequency, at low omega, and at high omega, although you change the damping ratio, it doesn't affect the magnitude of the frequency response function. And what you can see more is the magnitude equal to 1 at low frequency, and the magnitude turn to 0 at high frequency, which means that if the frequency of the force that you apply to the system is low enough, the magnitude of this and multiply by k, the magnitude will be 1. And if the frequency is high enough, the magnitude will close to 0. We cannot see, how to say, yeah, we need to go back to the physical meaning of this frequency response function. This frequency response function try to relate the magnitude of this is try to relate the, let me check here. Yeah, you need to go back to see the physical meaning of this. The magnitude of the frequency response here is try to relate the output by the input. So yeah, if the magnitude of this is 0 or 1, it means that if the magnitude of the frequency response is 0, it means that although you put a high force, it's no displacement happen in the response. And if it means 1, it means that the displacement and the force has the, how to say, the direct relationship. But don't forget that in the plot that we plot in MATLAB, we multiply the frequency response function by a spring constant k. So it makes sense if this is equal to 1, it means, yeah, you're gonna multiply the spring constant somewhere on the numerator, and f equal to kx, so it makes sense that the magnitude will equal to 1. But what we can read here is that at low frequency, the force and the displacement will be F equal to Kx. If your force is slow, your system can follow the excitation. And yeah, X and F has the same frequency and always has a linear relationship with a constant K if your system moves very, very slow. But if your system, if the force that apply to the system if the force that apply to the system has very, very high speed, high frequency, imagine that you have a spring mass system. You have a spring and mass system like here, and you have F. That is sinusoidal force. Yeah. If your force have a very, very high frequency, this means that you try to put the force to the right hand side, left hand side, right hand side, left hand side, very fast. In that case, your system has the effect of the inertia and cannot follow the input. So although you change the direction of the force very fast, but the effect to the displacement of the system doesn't appear. So what you can read from here is that at low frequency, when the force applied with a very, very low frequency, very slow, the displacement has a linear relationship with the force. But when the force applied with very, very high frequency, the displacement doesn't even follow the force. And what we can see at the natural frequency, when omega divided by omega n equal to 1. So when the force applied at natural frequency, when the damping ratio is more, the magnitude is high. You may try to do it by yourself when the damping ratio is equal to 0. You may try to do it by yourself when the damping ratio is equal to 0. The magnitude here will go infinite, which means it's the situation of the resonant frequency, which means the magnitude of the output X is go to infinite, although the magnitude of the applied force is bound or is limit at F0, but X go to infinite at the natural frequency. It will happen when the damping ratio is equal to 0. And what you can see here, one more thing that you can see here is when the damping ratio increases, you're going to have a smaller magnitude. And the last thing that we can observe here, is sometimes we can see the peak magnitude. For example, when the damping ratio is 0.1, we can see the peak magnitude here. And when the damping ratio is 0.5, we may can see a peak magnitude here. So we can see that the peak magnitude appear at one frequency, and it depends on the damping ratio. So how can we find the frequency that we can see the peak magnitude? We need to go back to the damping, the magnitude of the damping, the magnitude of the frequency response function is equal to 1 divided by square root 1 subtract by r square plus 2 psi r square. So if you want to find the peak magnitude, the thing that we need to do is from calculus, if you want to find the peak, you may need to divide the magnitude by the r, and at the peak magnitude, the slope of the magnitude against the ratio r, the slope should be 0. So how can we find the derivative of the magnitude against the ratio r? Yeah, this one, the power is -1/2, right? The square root is power 1/2, and this is the denominator of the square root, so the power will be -1/2. So yeah, to find the derivative of the magnitude of the frequency response function, we're gonna find the d by dr of the function 1 subtract r square plus 2 theta r square, and this will be power -1/2. So it should equal to -1/2 of this and the power will be -3/2. And we need to find the derivative of the inside things here also. So for the first term, it's gonna be 2 of 1 subtract r square. And you still need to find the derivative of the minus r square, which gonna be -2r. This is for the first term. And for the second term, you're gonna have 2 and 2 psi r. And div of 2 psi r by dr, you're gonna have 2 psi. This is for the second term. And this should equal to 0. This should equal to 0. So this one will be the denominator, so we don't care. So we're gonna check only this. And yeah, what we have here. So finally we have minus 4r plus minus 4r plus 4r power 3. And this will be 8 theta square r plus 8 theta square r equal to 0. Yes, it's a long thing, but we almost done. Finally, we have 1 subtract by r square, and 2 theta square is equal to 0. Yeah, so where should I bring it to? Okay, I'm gonna bring it to here. So if you solve for r, you may find that r equal to the square root of 1 subtract by 2 of damping ratio square. Okay, so the ratio r that we can find the peak value, the ratio r that we can find the peak value is depend on the damping ratio. It corresponds to the damping ratio by this relationship. And there is a case that we can find the ratio r and cannot find the ratio r. We can find r. We can find r just only if the terms inside the square root is more than 0. I'm sorry. We can find r, which means that the damping ratio should be between 0 and 1 per square root 2. So yeah, to sum up, we found that there is a ratio r that corresponds to the damping ratio that we can find the peak of the magnitude plot, and not for all the damping ratio that we can find the peak. Just only when the damping ratio is less than 1 per square root 2, or in this plot, it means the yellow one. If you see when the damping ratio is more than 1 per square root 2, for example, if the damping ratio is equal to 1 in the purple plot, we cannot find the peak magnitude anymore. So yes, this is the conclusion of this slide. And yeah, before we have a break, this is an alternative method to obtain the frequency response plot in MATLAB. And we will go in the detail of this topic again when we talk about the transient response. So don't be worried, just see it. And I just want to know that we have alternative way to obtain the frequency response function and do the plot in MATLAB. Okay, we begin with an equation of motion, the simple equation of motion here. And I hope you still remember in your differential equation class, I hope you remember the Laplace transform. The Laplace transform of the differentiation, the first derivative is equal to the S parameter and one initial condition. And for the second time derivative, the Laplace transform, yeah, you need to review the Laplace transform in the second half of our class in the transient response topic. We need to use Laplace transform, but I think you don't need to review so much. I mean, I may put the thing that we need in the class, but if you need more extensive knowledge, you may go back to review. But I think, yeah, the second derivative, we have this s squared xs subtract by s x0, and the second initial condition. So to transform the time domain equation of motion, the time domain equation of motion, if we take the Laplace transform on both sides of the equation, we're gonna have, yeah, the x dot dot will be these things. So we're gonna have s squared xs subtract by s x0 and x dot 0. And for the second term, the first time derivative of the x, we're gonna have this. So it will be s xs subtract by x0. And the third term, kx, is just k and xs. And on the right-hand side, if we take the Laplace transform of the force, yeah, we still don't know the function, but it will be fs. And if we assume the system begins from x0 equal to 0 and x dot 0 equal to 0, yeah, our system may not begin from this, but we're gonna deal with a particular solution. We're gonna deal with a particular solution. And the particular solution, just consider the effect of the force, not the effect of the initial condition. So by this, we're gonna assume the initial condition will be 0 here. So yeah, very simple. And you just, yeah, you may memorize in the simple way. It just, if you have x dot dot, you just have the s squared plus cs and plus k of the xs equal to fs. And what I want to say is the transfer function in the S domain is equal to output divided by input. Output of the system is the displacement, and input of the system is the force that we apply to the system. So yeah, Xs divided by Fs is equal to 1 per ms square plus cs plus k. This is a time transfer function in the Laplace domain. If we want to find the frequency response function, the alternative way to obtain the frequency response function is to replace s by j omega. So if we replace s by j omega, what we have is 1 per m j omega square plus c and j omega plus k. And yeah, j square is equal to -1. So finally, you can get k subtract by m omega square and plus c omega j. This is the frequency response function. From the transfer function in the S domain, if you substitute the S parameter by j omega, you can have the frequency response function here. This function is the same as what you obtain from the conventional method here. It's the same one, identical. Actually, H omega, yeah, is the frequency response function. H omega or Hj omega is the same thing. Yeah, it's identical. And on this side, on the right-hand side, it are the same thing here. And yeah, before this, we know how to plot the magnitude and the phase of the frequency response function. Now, we also can find the magnitude and the phase of the frequency response function. And in the MATLAB, we also have a simple tool for you to do it, but it's slightly different from our previous plot. So let's say this is the last slide before our break. We have the mass, the spring coefficient, and the damper that are a constant that we put into the system. And there is a command. We set the variable, the name of the variable is num. Num is numerator, is equal to 1. And denominator, you put the denominator as array like this. But yeah, if you refer to the denominator in the function named transfer function here, the system is the name of variable that store the transfer function. We use the function name transfer function, and in the function, we put the numerator and denominator here, separated by a comma. If we want to see what is the sys, or what is the variable sys in MATLAB, the sys will store the numerator and the denominator mck, m, c, and k. here. And if you remember the transfer function here, the transfer function here equal to 1 divided by ms squared plus cs plus k. Yeah. In the MATLAB, you can form a transfer function by the command 3 line. You can form the transfer function. Or you may do it in alternative way. You may write down sys equal to transfer function of 1 as the numerator, and the denominator you have m, c, k. You can write it in this way also. If you put the comma, the MATLAB will just store the value and not display. If you don't have the comma, they will display the result that you put into the program. And by use the command body of sys, just put this command, you will see this. As a result, the body diagram has the magnitude and the phase of the h j omega. The magnitude is the magnitude of the h j omega, and the phase also the phase of the h j omega. And yeah, h is your transfer function here. And on the horizontal axis is also a semi-log plot, and the phase will be plotted in the degree. The phase angle here are the same with this one, identical. But for the magnitude here, the magnitude will be plotted in the unit of the decibel instead of the, how to say, non-dimensional unit. And in the normal scale, decibel is a kind of log scale also. In general, the decibel can be obtained from 20 log base 10 of the h j omega. So before this, when you do the magnitude plot here, the magnitude plot is just the function here. If you multiply by k, it will be dimensionless. But for the body plot, the magnitude will be plotted in the decibel. And decibel is 20 multiplied by log 10 of the magnitude. So on the vertical axis, now it's not the log scale, but the decibel itself is a log scale. So here you can see a straight line. A straight line here, you can see that it decreases every 10 times. Every 10 times of the frequency value. 10 times means from here to maybe here. Ten times, yeah. Yes, maybe, yeah, it's not that correct. This one will be minus 40 decibel per decade. Yeah, but the increase here, the change here in the log scale is linear. But if you see the change here of the magnitude change as a curve, and the slope is not constant. But if you plot it in the decibel, yeah, you may can see the constant slope here. It's just an alternative to use the Bode plot. And in the next class, I think we can see more the application of the Bode plot. But yeah, for today, just know that we have an alternative to plot the frequency response function. And we should have a break for maybe 10 minutes before we continue on the example. So I'm gonna stop the recording now first, and we're gonna meet again at 2:55.